So I'm a scientist and a politician, and I'm very honored to be speaking here at the Astrophysics and Space Research Conference. I have a PhD in astrophysics from Columbia University. I got that degree in 1970. And my thesis was developing the first model of a galaxy, numerical model of a galaxy that included gas and stars being formed. I then postdoced at the California Institute of Technology in 1970 through 72, where I worked developing theories to explain galactic evolution and quasars. Now, I think one of the most important things that I can tell you here is that in addition to STEM training being a great preparation for being a legislator, that political skills are also critical for STEM researchers, STEM professionals. And what I mean by this is that, well, I'll get into more detail, but you have to sell yourself, you have to sell your research, you have to convince other people that your research is good, and I'll get into some of the more details on that, but we're all politicians is what it comes down to. Research can also, just research can change public policy. I'm obviously now in an office which allows me to vote and make laws. However, as a researcher, I also was able to change the world in many ways. Then I want to talk about how the analytical skills that you gather as you are working in STEM can make for better legislation and also for judging the legislation of others. So these are the four topics that I'll be discussing. So when I say political skills are critical to STEM professionals, it starts with just doing your own research when you do your thesis. There's a lot of things you have to learn which are political in nature. One of them is to not overstate your research findings. And people are more likely to believe you when you're a scientist when you talk about the limits of your research, what you've proved, what you haven't proved, what still needs to be done. That isn't always the case for politicians. They brag a bit, but certainly as a researcher, when you're trying to get your research out to others, you have to be very careful what you claim. You have to give credit to others whose work you used to drive your own ideas further. And all of these help you sell your ideas to others. Again, that's politics. Getting your first professional job and jobs thereafter, selling yourself, convincing people that not only will you be able to do great research, but you'll fit in with others and that you'll be an easy person to get along with. Now, some of the really great and outstanding work that's been done, for example, in NASA, we have the Hubble Space Telescope. When I went to my first astrophysics conference in 1968, I heard Lyman Spitzer, and you probably heard also about the Spitzer Space Telescope that's looking at infrared radiation, and yes, it is named after Lyman Spitzer. He was the head of the astrophysics and science and astronomy department at Princeton University. And I remember him talking in 1968. Now, the US had launched their first satellites just a decade before. They had some military uses, they had some scientific uses, but there really hadn't been any astrophysical and astronomical uses. That hadn't started by 1968. Nonetheless, Lyman Spitzer had the vision, and I remember him talking about the space telescope and what it could do. In those days, we thought the universe was somewhere between 10 and 20 billion years old. We didn't even know it to one significant figure. Now it's 13.8 billion years old that we say, and we seem to know it to 3 significant figures. But Lyman Spitzer in that conference, again, was telling us, well, we didn't know how fast the universe was expanding. For a number of years, they said it was expanding at 100 kilometers per second per megaparsec. And then Alan Sandage decided, well, maybe it was 50. Turns out the number's closer to about 70. But at that time, it really was very difficult to know how fast the universe was expanding. And he pointed out that with a space telescope, you'd be able to see individual stars in foreign galaxies, and in particular, a type of star called a Cepheid variable, whose the timescale of its pulsations, it's a pulsating star, was proportional to its luminosity. So you could look at these stars in other galaxies, determine how far the galaxies were away, and thus determine how fast the universe was expanding, get some much better idea of what the age of the universe was. I think the most spectacular use of politics for selling an idea is that of Kip Thorne from Caltech. When I was at Caltech, there was a scientist from University of Maryland who said he had detected gravitational waves. Most people did eventually reject that claim of a detection. But I remember Kip Thorne telling me over lunch one day that if the idea was correct, that person should get a Nobel Prize. As a result of that work, where someone was saying that they could detect gravitational waves, Kip Thorne over the next decade worked hard, this would be through the 70s and early 80s, to see if there was a way to, in fact, detect gravitational waves. And he eventually came out with the LIGO program, which you all know has been detecting collisions of black holes, of neutron stars, etc. But it took about 40 years of development to do this, 40 years of engineering. And $1 billion was spent, and theses were done on the ability to build this for many, many years. And yet there was no data coming out. And only a great leader could really keep us going, keep the $1 billion or more that went into this program flowing. And that was Kip Thorne. Like Lyman Spitzer, who got the Hubble Space Telescope up, you really have to point to the leadership of Kip Thorne. Now, he's very humble and says, oh, so-and-so has the engineering ideas, and so-and-so did this, and so-and-so did that. It was really Kip Thorne who kept the attention of the scientific community on this. And then just research itself can change public policy. And the greatest example of this is climate research. So I was involved in climate research in the early 1970s. I developed the first NASA climate model at the Goddard Institute for Space Studies in New York City. And I did work, for example, to show that the biosphere and the climate are coupled. And we were looking at, with Jewel Charney, a very famous meteorologist, we were looking at the advance of deserts. And what we showed is that as it got drier, if you overgrazed the land such that you got rid of all of the vegetation, then the vegetation wouldn't put water into the atmosphere. And if you didn't get water into the atmosphere, you didn't get rain. And so you just increased the desertification. And when we were looking at greenhouse gases at the time and how they might change the climate, and our models were quite primitive. So we really, it was clear to us that greenhouse gases would heat up the atmosphere. But what wasn't clear was how would the atmosphere react? And one of the ideas was, well, maybe the climate is very stable. And if you heat up the atmosphere, it'll just result in more clouds being formed. The clouds will then cool things off by reflecting the sunlight away from the Earth. That was where we were in the 1970s. We couldn't say for sure whether or not greenhouse gases were actually going to warm up the planet. It could happen in our very limited models, but we didn't have any of the natural feedbacks. Well, since then, there's been a tremendous amount of work, first of all, in paleoclimate, with various indicators showing that the atmosphere, in fact, has changed quite a bit. And the climate is not stable. In fact, it's unstable. And just very simple things can change it into one direction or another. And in fact, even though we've produced far fewer greenhouse gases than was calculated back then, that the climate has changed much faster because, in fact, all the feedbacks are positive. As you heat things up, for example, you melt the ice, you therefore go from a white surface to a dark surface like the ocean or the tundra, and it absorbs more heat, not less. To the extent that there is a feedback with clouds, it looks as if, again, that's a negative feedback. So climate's actually changing a lot faster than we ever thought it would back in the 1970s. Now, another thing that's very important, and although I started working in climate research, in the 1980s, a lot of that climate money was taken away by the Reagan administration. And as a result, there wasn't money to do research in climate, so I went into the nuclear weapons program. I became the United States expert on foreign nuclear weapons programs. So I would sit around the table with people from the CIA, the NSA, the DIA, all of these intelligence agencies that have spies and do communications intercepts. And they would say, here's what we've heard. And I would say, oh, this means that North Korea has gotten this far in its nuclear programs. And I do estimates of how many nuclear weapons North Korea could have, given how much fissile material we knew they had. The next thing I did was get involved in the negotiations for the Comprehensive Nuclear Test Ban Treaty. The treaty itself had reached a deadlock, and the deadlock was over what the limit should be on the amount that could be tested. And I don't want to get into all the technical details here because some of them are actually classified, but different countries were saying, oh, there should be a limit of this size or that size. And it went from pounds equivalent of TNT to tons of TNT to hundreds of tons, etc. And everybody had a different idea. And what I did was suggest that the best limit that everyone agreed to was 0. And this particularly, of course, pleased the developing countries, which did not have a nuclear program. Had we gotten a limit of hundreds of tons or a kiloton, they wouldn't have felt that this was actually a test ban. When we went to 0, all the countries, the nuclear countries and the non-nuclear ones, accepted this. I also developed a process called PIT. The PIT is the plutonium part of the nuclear weapon. It's called a PIT because it's hard. And it's in the middle of the bomb, like a apricot pit or a peach pit. Anyway, I showed that we could reuse our plutonium parts, and that way we closed down our petroleum fabrication facility, which had already had a major fire, which had threatened it was right outside of Denver, and it threatened to send plutonium oxide across the Denver metropolitan area. From that time, all the local folks wanted it closed, and they stood in front of trains and everything else. And what I did was to show that we could just use the parts we had already. So the most common question I ask is, how does a scientist become a politician? Well, first of all, I've always had an interest in politics and policy. I think it's because I was the oldest of a family with 7 brothers and sisters, and I was just used to taking responsibility. So I worked on political campaigns, and these are some of them. I became a union representative. I became the PTA council president. I recruited and managed volunteers for the local Democratic Party. I then got involved with school and council commissions and eventually ran for Hayward City Council and became an assembly member. As an assembly member for the last 8 years, I've been chair of the Assembly Committee on Public Safety that deals with crime and punishment, been the chair of the Assembly Committee on Environmental Safety and Toxic Materials, and members of the Appropriation, Public Safety, Revenue, Tax, and Utilities and Energy committees. So what is it like to get elected? Well, the main thing is to work hard. And of course, all of us STEM folks know how to do that. I developed a team of professional advisors, got a political consultant, a treasurer, a fundraiser, and I did what the expert told me to do, and I outworked everyone else. The only thing you really need to do to run for office is meet voters and raise money. So I contacted voters between, well, it's 6 p.m. to 9 p.m. US time, 1800 to 2100 hours, Monday through Thursday. Friday night I took off. I walked precincts from 10 a.m. to 5 p.m. That's 1000 hours to 1700 hours. On Saturdays, took Sunday off and walked from 1 o'clock to 7 p.m., 1300 to 1700 hours. The point is work, work, work. That was really what got me elected. I am the only scientist. And people said about me, my staff in particular, with Bill, the easy things are hard and the hard things are easy. What they meant by that is, well, I had some political skills. They weren't nearly up to what they could have been. In particular, I backed the wrong person to be the party leader of the House, the Speaker. But with Bill, the hard things are easy. They hardly ever had to brief me on anything. I just ever read things ahead of time and I would know all the facts. As a scientific approach to policy, data and research guide my every decision. So I will find out what really this legislation will do. Now I have friends who say, oh, the environmentalists are for this, therefore I'll be for it. No, I will look at what I believe the legislation will really do. And sometimes what the environmentalist wants will work, and sometimes it won't. The other thing is on complicated issues, I was dealing with the privacy issue with the Google Android system. And when I first went to talk to them about this, and I had legislation that they didn't like, they sent all of the government relations people, and I told them, look, this isn't going to help. I want to come back and I'm going to talk to the engineers. And I talked to the engineers and they said, oh yeah, we can guard people's privacy if we do this, this, and this. And they did it, and I didn't even need the legislation. My staff and I always ask a lot of questions. And one thing that happens as a result of that is people don't often bring me legislation. Lobbyists don't often bring me legislation because they know in the end, I'm going to decide it's my legislation. And if they don't, even if they've brought the legislation to me, I may change it in a way that they don't like. So one of the most important things I do here is chair this committee, Environmental Safety and Toxic Materials. And as I'm looking at papers, I'm able to read about what really is going on. So PFAS, these are the fluorinated chemicals, of which there's a lot of concern right now about water pollution and such. Rodenticides. We got a bill through our committee, which very much limited the rodenticide uses because the animals that feed on them were dying. In particular, all of the cougars in the mountains here. Question of whether or not flame retardant should be used, toxic in cosmetics. And then I love to have hearings where we look and try and determine what is going on. And in particular, I've done a lot of work on lead testing and prevention of lead poisoning in children. But I've done other things that aren't particularly scientifically related. I have a bill that said you can't hold your cell phone in your hand because if you do, you'll get distracted. I had a bill on how to use animal-free testing determining whether or not it's hazardous, therefore protecting animals. Recycled water, lead testing in children, algal blooms. Policies on use of drones and how the film from these can be used. So at this point, I'm willing to open it up for